This is the present video presentation of my project for this AI and ML course. The project title is Polynomial Contrastive Learning for Privacy Preserving Representation Learning on Graphs. It's a long title, but I'll break it down thoroughly in this presentation. Okay, so let's get into it. Right, so the outline, I'll start with the introduction, then I'll give some, specifically the motivation behind this project. Then I'll go over through some background. Like I'll set a baseline so that you guys can follow along the core idea of this project and the core implementation and the core research contribution. Then the core part of this presentation is the methodology. Uh, like development of this polygrace framework. I'll explain it. What is this framework? Then I'll share my experimental results. What results I got from all the experiments which I performed. Then discussion of these experimental results and some future work which I intend to do in the near future only. Then I'll conclude the presentation after it. Okay, so first I'll discuss this, like the motivation part, the and what I call the power and privacy paradox. So let's talk about graph data. Like I know that like there's data everywhere, but specifically in data, if we categorize them, one category comes out to be the graph data, and it is everywhere. Like as mentioned, we have social networks, we have molecular structures, we have financial transactions, medical records. All these are essentially graphs, right? Uh, but the challenge is, or I should say, their trait is, valuable data is sensitive. Obviously, very obvious statement. Cannot be shared freely. Like for example, like take financial transactions or financial records for example. Let's say there's like some big high trading company like Goldman Sachs. They don't want their data to be publicly open or like very easily available, so like so that they end up helping their competitors like JP Morgan and all, right? So it cannot, obviously we cannot shed freely and even cheaply. uh, then we have privacy regulations. Like each country has their own regulations and they do not go easy on them. Countries especially like in case of defense and even their research, like ISRO and all, space organizations, they don't want their data to be very easily available to other countries and maybe some other private organization too, right? So, problem one, the two key problems in modern machine learning on graphs. So, one is data scarcity. So, label data, like we all know what label data is. Label data is usually required for traditional training methods. It is labeling data is it's especially in graphs where we have like these huge amount of nodes and each node is connected. Like it can be connected randomly, but like it's harder to label than normal data set. It's obviously expensive and time consuming. We require huge amount of time, we need huge amount of workforce, and that obviously gets expensive. So the solution is like this very clever uh, approach, and I should say very clever field of self-supervised learning. So learning from unlabeled data is the motivation and the goal which this field of SSL tries to achieve. And in this, we have this GRACE framework which achieves quite good performance. And the problem too is the data privacy. Obviously, like as mentioned earlier, the fields which I mentioned, the molecular structure. Maybe there's some pharma company developing some novel drug. They don't want other organization to get their data because obviously it's not like private research, highly sensitive research. Same goes with finance and defense. So data privacy is obviously a problem. Sensitive graph data cannot be shared with third-party models. And during in majority of the training process and even inference process, the process of inference, It requires access to plain text data. So if we want some company or some third party model to help us help them during their research and work, they will need to give their data. But this is exactly the problem. They cannot just give their data because it's very sensitive and private. So the solution is homomorphic encryption. Homomorphic encryption, the higher level ideas, enabling computation over encrypted data. So I'll give a very high level idea. Just like how RSS system is based upon this problem of prime factorization. We can what in past years what mathematicians and cryptographers have done is they've taken other like this very elegant problem, learning with errors, and they've built provably secure and even quantum secure uh, crypto systems over that problem, which also happen to be fully homomorphic. So no, like a computation over this encrypted domain obviously will never expose the raw information. But the main problem is it only supports polynomial operations. So let's look into more details of this. So yeah, homomorphic encryption supports only polynomial operations, only polynomial friendly operations. And what do I mean by this polynomial friendliness? So, I can easily add two polynomials. I can multiply two polynomials. I can raise a polynomial to some integer power, like two and three, right? And everything, and that's it. Everything else is just not polynomial friendly. So, and standard trace framework, it uses all sorts of these non polynomial friendly functions. So we have the very famous ReLU function, activation function, which is essentially just the max function. Is obviously not clearly not polynomial friendly. Then we have the L2 norm, X. We have division again. Then we have the non-Euclidean norm. Again, we take the square root at the end, so not friendly. Then we have the soft max function. We have division. Then we have exponential, no go. We have division operations other than these three highly non-polynomial friendly functions. Then we have exponentials again, e to the power e to the power of the input. Then we have square root. So Grace is fundamentally incompatible with HE. So if we want a secure SSL framework over graphs, we need to develop a whole new framework other than Grace. But it can be inspired by Grace, and actually, I did get most of my inspiration from this existing framework only. Okay, so my contribution, the PolyGrace, a fully polynomial friendly self supervised learning framework for graphs. So, key innovations. One, I replaced ReLU with X squared activation. Actually, this was I took inspiration for this from this very famous paper by Microsoft on CryptoNets, in which they propose that we can replace this ReLU function with such x square and higher order polynomial activations. Then we have then the main, like which required the most thought and uh, extensive trial and error, is the novel polynomial loss function. So it is margin based, contrastive loss, using only additions and multiplications. And third, I got pretty competitive performance compared to the standard case on existing on benchmark data sets. Right. So the main result is privacy preserving graph learning without sacrificing the performance. Right. So let's first that was the background for the project. Now let's see. That was the motivation behind the project. Now let's get into the background. So first, graphical neural networks. So it was first introduced by Gibbs and Welling in 2017. Is the foundation of modern graph learning. So the key equation shown here. It looks complex, but it really is not. So each layer we have a neural network which with layers in it. So each layer computes new node features. So it kind of accumulates information from their neighboring nodes. Then we have HL is it is the node feature matrix for the layer L. Then ATILT is the adjacency matrix. Okay. With self-added loops, D is the degree matrix, T tilde is the degree matrix, W is a learnable weight matrix, which we will try to optimize, and sigma is a nonlinear activation function, and usually it is ReLU. So the elegant idea behind this graphical neural networks is that each node's representation is what can I say is updated by uh, collecting and transforming the information from its local neighborhood. So after two layers, let's say after like for example after two layers, each node will have information from its to second degree neighborhood till its second degree neighborhood. So this message passing mechanism is what makes these graphical neural networks so powerful. So a standard two-layer GCN looks something like this. So first we apply the GCN layer, then the activation, then second GCN layer to get the final embeddings. Right. So this is the standard GCN implementation. So uh, this is like the traditional uh, implementation for this encoder function. But a main point of focus is this use of ReLU, as mentioned again. It is a non-polynomial activation. Right. So let's move on to the next slide. Right. So race framework. So let's now that we know what a GNN is, what a graphical neural network is. Now let's see what exactly is the Grace framework. So as mentioned before, it is self-supervised learning on graphs, and it works through three steps. Like there are three major steps into it. So first, we create two corrupted versions of the original graph. Then we randomly drop edges with probability, usually taken zero point 0.4, and randomly mask node features with probability zero point 0.3, usually. So these augmentations kind of preserve the essential structure while adding noise into the data sets or the graph. So, it kind of so the main idea is to force the model, is to make the model learn these robust representations. Then we have like the encoding, the GCN layers. So we have these different skewed or augmented views from the previous step. Then we pass them through the same encoder to get our embeddings Z1 and Z2. Then we have the contrastive loss. This is where the optimization happens, or uh, in words of animal, the learning happens. So for each graph node I, the embedding from view one, here's the main idea behind this loss function. So embedding from view one should be similar to the embedding of the node from view two, right? So these are like the positive pairs. Uh, but the thing is, it should be dissimilar to embeddings of different nodes. So we have similar nodes and different nodes, and and in both of these, like the structure overall is to very low degree a little bit skewed. So like different pairs should be marked negative. So by maximizing agreement on positive pairs and minimizing it on negative pairs, the model learns meaningful representations, and the result is powerful. We learn high quality node embeddings without any labels whatsoever. Right now, this is like the standard uh, info NCE loss, which is used in this framework, and this shouts non-polynomial friendliness. So we have cosine function. We have like cosine function is hidden in this dot product. Then we have division, we have exponential, we have logarithm, we have whatnot, we have square root, highly non-polynomial friendly, right? And this is like the Grace loss implementation. Obviously, like we will not be dealing with this at the end of with the code with the project scope, but this is how you would implement this this beastly looking function, right? So let's get into the third area of this background, that is homomorphic encryption. Right. So key concept is computation on encrypted data. So modern edgy scheme. So like the LWP problem which I mentioned before. So there are various schemes built around it. We have BFV, BGV. We have CKS, which I'm dealing with. There's also TFAG, but we don't have to worry about the other schemes. Right. So there are so the modern energy scheme, homomorphic encryption scheme, majorly aims for enabling two core operations for us. That is the addition and multiplication. So uh, like a scheme is called fully homomorphic if these as long as these two operations are supported. So the problem, like obviously, like there has to be some trade-off because why not? So each multiplication increases noise in ciphertext, uh, and noise rows multiplicatively. That so this multiplication operation is more expensive than this, more expensive to the ciphertext, and also the and also computationally. But we don't have to deal with this. We'll deal with that problem here. The problem which we have to deal with is uh, uh, the noise growth of the ciphertext itself. So uh, it is more expensive within the ciphertext. Then too much noise, it will, like after a certain degree, decryption will fail. And so there's like we while designing the system, we can beforehand decide the multiplicative depth. So the max sequential multiplications. And obviously, like if we have like more the number of multiplications, more will be the noise, and more will be the amount of resources used, because more multiplication that will obviously come with some price, if not very expensive price. It happens to be quite expensive, but there is some price. Okay, so the design principle. So first we have to make things polynomial friendly, and on top of that we have to make things noise friendly too. If we are at the end uh, integrating the framework with an FHE scheme. Right. So let's move on. This was the CryptoNets paper I previously mentioned. It was published by Microsoft. Like this guy, Kyle Buckrock, uh, was an engineer at the time at Microsoft. So in that, they mentioned that one can think of like replacing this ReLU function with the x square or even higher degree. In this case, I used x square because obviously lower degree and lower multiplication depth. So right. So my approach was to take uh, inspiration from this CryptoNets paper, then address more. So the CryptoNets paper dealt with CNN inference, and the problem which I'm dealing with is a learning problem. So it is obviously different from the CryptoNets. And obviously like more challenging problem. Inference is a one-time process, and it's very deterministic, but chaining gets very messy. And it's kind of the like I browsed through a huge amount of literature, and this is the first work on HE comparable SSL for graphs. So this is the pipeline. So we have the original graphs. There's this augmentation process. Then we pass them through our polynomial GCN encoder, both of them parallelly. And in this process, in this like from this augmentation and passing through this encoder, the encryption, this homomorphic encryption is happening. So these view1 and view2 are actually encrypted views, not plain text views. Then we produce our embeddings, then we pass them through polynomial loss, uh, then like the training happens, and during the process, that like the privacy is never really sacrificed, right? So innovation one is the polynomial GCN encoder. So mathematically, the second hidden layer is computed as the first graph convolution produces intermediate features. Then we square them element wise, then apply the second graph convolution. So the design rationale is important. So x squared is non-linear. Uh, this is crucial because like a linear activation would collapse the network into a single linear transformation. So I had to go for a non-linear activation function, and while keeping the noise growth problem in mind. So it's efficient for HE because squaring, like obviously, causes minimal noise growth compared to higher degree polynomial, and it's directly inspired by the cryptonet's principle. The mathematical form is shown at the bottom. We compute A-tilde times squared output of the first layer, then we multiply by weights. So purely polynomial, very polynomial friendly, right? This is the implementation. Nothing special in it. Like I just had to replace ReLU with X squared. Uh, then the impact of this step was fully polynomial computation graph. Right, now let's move on to the next slide. Now this is the innovation tool which required the most thought and the most effort. So this, as mentioned before, is the standard Grace loss, and it uses softmax and cross entropy. So we see all these logarithm exponents, and within these like this cross entropy, we have whatnot. We have dot products, cosine functions, we have square roots, so not HA compatible. Okay, so this is the thing which I came up with. So it is like margin based square distance. Uh, Now let's break it down very carefully. So the first term is the contrastive component. So for each negative pair, we compute this difference between negative similarity and positive similarity, and add some margin which one has to tune, and then square the result. So far we have addition and multiplication polynomial friendly. Uh, so why did I do that? So if you look very carefully, if you like analyze this equation, if you think about it, it penalizes cases where negative pair similarity is not sufficiently lower than a positive pair similarity. So the margin provides a clear target. Negative similarities should be at least m below the positive similarities. Now this and like there's this second L2 regularization term on embedding magnitude. So you like one might see that I'm at the end taking norm, but I'm taking norms like Euclidean norm squared. So I'm removing the square root from it. So I'm just squaring and adding the vectors. So it serves two purposes. It prevents embeddings from growing from exploding during the training process. And it, like as mentioned, it is very like edge is obviously on not on the edge but near the considerably near the edge all the time because of this noise. And during this training, if this training process also like decides to be not noise friendly, it's obviously it will obviously be a huge problem. So so it keeps growing from unbound training, and critically for edge, it keeps values small to minimize noise growth during encrypted computation. And again, like yeah, we have all polynomial friendly operations. So let's get into more mathematical details of this polynomial loss, because why not? So similarity matrix, this S is the matrix product of Z1 and Z2 transpose. It's an n by n matrix where each element ij represents how similar node I is from U1 is to node j from U2. So the contrastive term on the diagonal versus off diagonal elements. So like the diagonal elements should be ideally high and non-diagonal should be ideally zero, or as low as we can go, so like -1. Why not? So S I on the diagonal is positive pair similarity. We want this high. S I J of diagonal is negative pair similarity. We want this low. The margin M, typically in my experiments, I set it to 1, specifies how much lower do we want it, how much lower, how much difference we want to have. So we compute Sij minus Sii plus M, and then we square it to amplify the difference from a higher level view. So Si is at least m greater than Sij, so this difference is negative, but squaring makes it small, so low penalty. If negative similarity is too high, this difference is large and positive, so leading to high penalty after squaring. So intuition is clear: positive similarities should exceed negative similarities by at least uh, the margin m. This directly encourages the contrastive learning objective to make similar embeddings, similar embeddings more similar, and dissimilar embeddings more dissimilar, but using only polynomial operations. Right, now let's move on. Right, the regularization term, the second part of it. The regularization term obviously deserves special attention. So we compute the Frobenius norm squared of the embedding. So Frobenius norm is square root of sum of all squared elements, but we use the square version, which is simply squared of all elements, no square root, and like polynomial compatible. Then expanded out this lambda times average L2 norm squared of all node embeddings from bottom views, like the expanded form. The purpose is threefold. It's a standard L2 penalty preventing from overfitting. Then it prevents embeddings from growing unbounded, which could cause chaining instability. And most importantly, for homomorphic encryption, smaller embedding values lead to small store noise growth during encrypted multiplication operations. So when you multiply ciphertexts, encrypting small values, noise grows much slower than when multiplying ciphertexts, encrypting large values. So this regularization acts as a polynomial substitute for the L2 normalization that standard trace framework uses. So instead of normal embeddings to unit length, we softly constrain their magnitude. Right. So this is the polynomial loss implementation. So if one looks over at line 3, We compute the similar matrix through matrix multiplication. Lines, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Uh, Extract the positive pair similarities from the diagonals. Then lines after it, after the next comment, compute the margin-based differences for all pairs. Then line after that, we mask out the diagonal to focus only on negative pairs, then and square the differences. Then we have the L2 regularization as mean of sum of squared values, right? And then finally, in the final line, we return the total loss as sum of contrastive term and regularization term. So every operation is either matrix multiplication, addition, subtraction, squaring, mean, everything good so far. Right. So this is the comparison table of grace and polygrace. So this table lists like is directly comparing them. So both use matrix multiplication. That's fine. But grace uses the L2 normalization, requiring square root and division. We completely neglect this. Uh, then grace uses division by temperature. We avoid division, obviously. Then Grace uses exponentials in softmax. We use none. Grace uses logarithm in gross entropy. We use none again. Uh, Both use squaring, which is again like polynomial friendly. So doesn't matter. So the bottom line is Grace is not HE compatible at all, and Polyloss is fully HE compatible. And interestingly, I did some math behind it, and the computational complexity is similar in both cases. So both are equally expensive, computationally speaking. But the only difference is they fundamentally use different operations. Uh, right. So next we move on and do some analysis for HE part, homomorphic encryption part. So multiplicated depth is the maximum number of multiplications in the whole process. So we have like this is the depth analysis. So in the encoding layer we have depth one, in activation layer, just a simple x squared. We have we get 2 degrees of depth. Then in the GCN layer we get 3 degrees of depth. In similarity we get uh, depth of 4. In loss computation we have depth of 5. So at the end, we only have to deal with uh, 5 degrees of multiplicative depth, which is very doable considering modern HE libraries. So as mentioned, they like modern libraries can support depth up to 10 to 20 very efficiently, and we only have 5, so it's a very good sign. Okay, so right. So noise growth in CKKS is like for ciphertext encrypting values V1 and V2. So when we add two ciphertexts, the resulting noise is just the max of which one contained the more noise. And if noise are very similar, then we don't have to worry about any increase in noise. But the main problem is with this multiplication, and you can see noise grows much faster when multiplying larger values. And these, at the end, it would depend on the magnitude of the encrypted values, as you can see here. So, how this framework manages noise? So, x squared instead of high degree approximations. Then we have L2 regularization, which keeps embedding magnitude small, and we do no normalization. So the thing is, we can actually do division operation, but it is just too expensive and impact and resource intensive to even think about it practical systems. So this is the graph augmentation implementation. Uh, Now we slowly move on to the experiments part. You can go through this code, nothing special into it. So the experimental setup, right? So we evaluate on three standard network benchmarks. So one is Cora, which has 2708 nodes with 5429 edges and 7 classes. Uh, then we have side steer with similar size but different structure. Then we have PubeMed, which is a much larger with nearly around 20,000 nodes and 44,000 edges. So we compare again against two baselines. The unchained encoder with random weights gives us lower bound, and then how well you can classify with no training. Then the standard grace with ReLU and contrastive loss is the upper bound, the best non-private method. So our evaluation protocol follows standard practice. We train the encoder using SSL for 200 epochs. Then we then freeze the encoder weights. No fine tuning. I did not go into the fine tuning part. We train a simple logistic regression classifier on top of these frozen embeddings using the training set. Then finally we evaluate on the test set and report the accuracy. So this tests how good the learned representations actually are. Right. So let's move on to the configuration details. So here are all the hyperparameters for reproducibility. Uh, So our encoder has two GSIN layers with hidden dimension 64 and output dimension 128, and dropout rate is 0.5 to prevent overfitting. Then we train for 200 epochs with learning rate 0.001 and weight decay like 5 into 10 minus 4 for regularization. Then you can see all these details further. I'm not dictating all of them one by one. And these are like the the result, the main result. So on Quora, and we get some very interesting results. So on Quora, the untrained encoder achieves 54.6 accuracy, not much better than random guessing for 7 classes. Then Standard Gray achieves 82.6, a massive 51% relative improvement. And the polynomial case achieves 79.7, which is very small margin compared to standard grades. So let's put this into more perspective actually. So we are only 2.9 percent points behind Grace, which is around 3.5 relative drop. And for fully HE comparable method, this is remarkable. On site steer, something even more interesting happens. So Unchained gets 47 for 48.7, Grace gets 66.6, and Polynomial Grace got 67.8, which outperformed the non-private baseline by around 1.2 percentage points. So I know that I cannot just conclude that uh, polynomial grace is better than grace for this particular data set, but I can easily argue that it is at least as good with the results I got. Then, but on PubeMed, I faced some challenge, and that was the accuracy dropped to 51.3 compared to Grace's 79.6. This is very significant degradation, and it did give me some insights. So like. This framework, which I developed, is highly effective on smaller graphs but faces larger and denser structures. So this is a research problem which I will obviously work upon. I have intentions of working upon in the future. Right. So these are the key insights. Nothing which I did not mention before. Right. So I did some more experimentation. So now, let's get into get into some visuals. So here I used TSNE to project the 128 dimensional embeddings down to 2D for Cora dataset. So on the left is standard grays, on right is polygrays. Each color represents a different research topic class. Right. So the key observation, both methods produce well separated clusters. You can clearly see no nodes you see that nodes of the same class are grouped together with distant boundaries between classes. The polygrace embeddings on the right are quantitatively comparable to grace embeddings on the left. The clusters are similarly tight. The separations are similarly clear. This demonstrates that polynomial grace is learning meaningfully, discriminatively, and uh, yeah, by only using standard polynomial operations. Then I again did ablation study too. This ablation study decomposes our contributions to understanding what each component does. So we test all four combinations of encoder type and last type. So standard GCN with grace loss is baselined at 80.8%. Standard GCN with a polynomial loss achieves 82.8%, the best result in the table. This is obviously like much fascinating. It shows that a polynomial loss function is not just a compromise for HE, it's actually a powerful objective function on its own right, even without HE constraints. Like even if we have maybe like plain text data, why not go for it? Then the poly-GCN with grace loss gets 81.2%, showing X squared activation is a viable replacement for ReLU and with only minor impact. Then full polynomial grace with both components gets 80.8%, matching the baseline. The key insights are polynomial loss function alone improves performance by 2 percentage points. The polynomial activation has minimal impact, only 0.4% with grace loss. Uh, the combined system maintains strong performance, and both components very effectively integrate to create a fully HE comparable framework without any accuracy loss. Then, like you can see the analysis of parameter sensitivity. So this is also again a critical experiment for practical deployment. So the plot which you guys are seeing is uh, shows how performance is varying with the regularization parameter, which is lambda on Cora dataset. I did perform on other datasets too, but I'm presenting only Cora here. So I tested five values spanning five different values of for lambda from 10 to minus 5 up to 10 to minus 1. So the key finding was performance is stable across a wide range from 10 to minus 4 to 10 to minus 2. We get consistently good results with around 80 to 81% accuracy. Then the best single value is about 10 to minus 2, achieving the best uh, uh, 81% accuracy. Then performance only degrades at extremes. So like too little regularization at 10 to minus 5 or too much at 10 to minus 1. The stability is important. It means that polygrace is not overly sensitive to hyperparameters. So we don't need extensive tuning process and any reasonable value in a very broad range, like 10 to minus 9, 10 to minus, very broad range. So this makes the practical method, uh, method practical and robust. Right, so let's move on to the next slide. So training dynamics. So this plot shows training loss curves over 200 epochs and for both methods on Quora. So the blue line is for standard trace, the red is for polytrace. Both methods convert smoothly and monotonically. There is no instability, no divergence, no oscillations. No. So this demonstrates that optimizing a polynomial loss is not problematic at all. We don't encounter any optimization difficulties. Then we have this is the training loop code. Nothing really innovative into this. Uh, but I will mention some key points though. The entire pipeline is differentiable in polynomial. So automatic polynomial differentiation works seamlessly. The gradient flow through all the squaring operations and matrix multiplications without any issue. This simplicity means polytrace is easy to implement and deploy. Then we have the evaluation protocols implementation. So we freeze the encoder in the evaluation mode, generate our embeddings for all nodes, extract the chain and test splits, train a scikit-learn logistic regression classifier on the training embeddings, and evaluate on the test embeddings. This is standard linear evaluation protocol, if you will, for SSL. It tests whether the encoder has learned useful or and transferable representations. And the fact that we achieve 79.7 accuracy with a frozen encoder and simple linear classifier shows that polygrace learns high quality features. Now we move on to the last parts of the presentation. So these are the theoretical insights of this polynomials. So polynomial case. So we have the polynomial activation, we have margin-based loss, and then we have L2 regularization. So this is the mathematical analysis I did on why this x squared term worked so well. So x squared is first, why did I there are even more benefits of not going for high degree approximations. So x squared is always positive, so we get stable gradients from it. It can produce XU can produce very large values, and it is obviously gets less stable with large values. Then we have empirical evidence that x squared works better in practice. So limitations and challenges. You can see here nothing which I did not mention before in previous slides. Uh, so the future direction one, actually I did work on it a little for like uh, and thought of integrating this into the existing project, but it got a little too complex. Mainly because I keeping the stability of the architecture itself, the transformer architecture itself. So, the high level view is that, for one, the attention function. It uses the softmax, square root division, whatnot. Then we have, I did work on this, on going towards a polynomial friendly, but I was not able to get very stable results out of the candidates which I tried. So this is the code for it. It will explode if you try running it. So do not. Right. So that second direction is to actually maybe take some real world data set. Obviously, I will not be able to get my hands on some very sensitive data set, but I can encrypt the normal code and PubMed data sets and use more like these modern libraries like Microsoft Seal, TenSeal, or OpenFHE for actually implementing an encrypted learning system. Then, like parameterization, I will need to perform more noise modeling from edge side, then performance optimization. So one thing about edge is its like highly active field in hardware acceleration and optimization in general. So I will obviously look like that's kind of my main interest, the hardware level acceleration of all these sorts of stuff. Then evaluation, like after performing all these, I will obviously perform vast experimentation and evaluation. Then third direction is broader applications. Right now, I'm like limited to very specific framework, but like my goal is to develop similar high performance and practical frameworks for making this learning and especially collaborative learning over encrypted data possible because it will be very useful for such like especially in medicine and pharma industry, right? So broader impact. Nothing special, like I mentioned a lot of times before, and in healthcare, finance, social networks, defense. So high amount of applications. Then this is also another idea which I got while pursuing this project is by actually developing a multi-party protocol, an MPC protocol on graphs. So multi-party computation is very interesting. So what happens is we are not encrypting the data. We can encrypt the data, but we don't essentially have to encrypt the data to evaluate some function without sacrificing your data's privacy. So people nowadays are collaborating such existing MPC techniques with homomorphic encryption to develop even more robust and secure data, like computation multi-party protocols, which can easily be integrated into this these self collaborative learning, or I should say federated learning frameworks. So that is also something which I intend on looking into. So this is the summary. You can go through it. These are the key technical achievements. Then key takeaways. Then yeah, final remarks. Polygrace bridges the gap between powerful representation learning and robust privacy guarantees. Uh, Again, the main achievements. Then, thank you.